Hello, welcome to our presentation. We are excited to discuss the various security threats of unmanned vehicles and drones. I am Morgan Franklin, and my teammates are Anthony Smith and Jason Green. In our presentation, we will discuss a brief background of the topic, followed by an overview of drones and attacks, the Internet of Drones, the big three areas of drone vulnerabilities, solutions for various threats, the gaps we discovered in our research, and conclusion. So starting with the overview. Next slide. I want to start by looking at the research questions we posed to ourselves when looking at the world of UAVs, or unmanned aerial vehicles. We wanted to dive deeper into what security threats are out there when it comes to drone platforms. Drone technology has had a stagnant and niche approach over the years since it first became relevant. The growing drone market is largely made up of photography and real estate and has stifled several other key areas of industry. Examination of the current state of the utilization of machine learning in the drone industry leads us to the preliminary conclusion that the drone industry is still an emerging market and has yet to reach its full potential. The main utilization currently outside of photography and real estate comes through military applications. This is due to a UAV both reducing the risk to a human pilot while simultaneously being more cost-effective. This has been widely demonstrated in the war on Ukraine, with whole drone divisions being created in the military due to the effective use of drones. The world of drones will become increasingly more and more reliant on the tether of communication. With drones pushing out farther, having longer flight times, and achieving more tasks, it becomes even more important to focus on the security of a drone's communication. The threats that are specifically targeting communications are also heavily focused on the integrity and confidentiality aspects of the communication in both the hardware and software components of a drone. The ability for a drone to carry out its mission task fundamentally lives and dies with the drone's ability to communicate. That is where our focus will be in this presentation. We will look at the overall literature of drone security and address the three major areas that need to be secured in drone communication, the hardware, and the software.
So UAVs offer a great market opportunity for equipment manufacturers, investors, and business service providers. According to the PwC report, the addressable market value of UAV uses is over 127 billion. Civil infrastructure is expected to dominate the addressable market value of UAV uses with market value of 45 billion. A report released by the Association for Unmanned Vehicle Systems International expects more than 100,000 new jobs in unmanned aerial vehicles by 2025. Global UAV payload market value is expected to reach 3 billion by 2027. Dominated by North America, followed by Asia, Pacific, and Europe. The payload covers all equipment which are carried by UAVs, such as cameras, sensors, radar, LiDAR, communications equipment, weaponry, and much more. Radar and communication equipment segment is expected to dominate the global UAV payload market with a market share of close to 80%. Followed by cameras and sensors with around 11% share, and weaponry with about 9%. Business intelligence expects sales of UAVs to reach 12 billion in 2021, which is up by a compound annual growth rate of 7.6% from 8.5 billion in 2016. The future growth was shown in three main sectors: consumer UAV shipment, which reached 29 million in 2021, enterprise UAV shipments, which reached 805,000 in 2021, and government UAVs for combat and surveillance, which the U.S. Department of Defense allocated a budget of 4.45 billion for. Now, it is unclear how much of those budgets were actually allocated towards security. There has been many research studies on unmanned vehicles that reported progress towards autonomous systems that do not require human interactions. In line with the concept of autonomy with respect to humans and societies, Technical systems that claim to be autonomous must be able to make decisions and react to events without direct interventions by humans. Therefore, some fundamental elements are common to all autonomous vehicles. These elements include the ability of sensing and perceiving the environment, the ability of analyzing, communicating, planning, and decision-making using onboard computers, as well as acting, which requires vehicle control algorithms. These systems are also known as connected vehicle systems.
Cybersecurity is one of the most significant challenges in the connected vehicle system. Connected vehicles are prone to different cybersecurity attacks that endanger passenger safety. Cybersecurity in intelligent connected vehicles is made up of in-vehicle security and security of inter-vehicle communications. Security of electronic control units, also known as ECUs, and the control area network, also known as CAN bus, are the most significant parts of the in-vehicle security. With the development of 4G LTE and 5G remote communication technology for vehicle to everything communications, the security of inter-vehicle communications is another potential problem. An introduction of architecture of next generation vehicles, driverless and intelligent vehicles is the basis of this paper. The paper also identifies major security attacks on the intelligent connected vehicles. These attacks provide a comprehensive survey of available defenses against these attacks and classify them into 4 categories. 4 categories are as follows: cryptography, network security, software vulnerability detection, and malware detection. Cryptography involves encryption that has been used by humans long before computer systems to hide messages from unwanted parties. As computer networks have developed, encryption has become an essential part in ensuring that the integrity of information remains intact. In intelligent vehicle systems, encryption is an essential key to ensure safety. Network security. Intelligent vehicles require cooperation from other devices and sensors to perform communications properly. These communications are implemented between the controller area network and the electronic control units. However, security mechanisms have not been considered in these settings. The CAN and ECUs are valuable targets for adversaries. For example, vehicles can connect to wired devices using USB, CD, wireless, such as 3G, 4G, Wi-Fi, and smartphone. And all of these make the car become an open system. Thus, it is necessary to invent suitable countermeasures to relieve the security risk in the intelligent car. Software vulnerability detection considers a number of significant and well-known machine learning approaches for software vulnerability detection, which are reviewed and compared with each other. Traditional approaches to software vulnerability detection are based on expertise. The work is tedious and achieves a high false negative rate. There are 2 available ways to apply machine learning and deep learning methods for software vulnerability. One is supervised learning approach, which creates a vulnerability prediction model and vulnerable code pattern recognition system using a label data set. For different methods, the key difference is the feature selection. Malware detection. Whenever something new and as complex as an intelligent car or truck connects to the internet, it is exposed to the full force of malicious activity. Leaving an attack surface unprotected will expose vehicles to many security risks, including malware and Trojans.
So the world of drones will become increasingly more and more reliant on this tether of communication. With drones pushing out farther, having longer flight times, and achieving more tasks, it becomes even more important to focus on the security of a drone's communication. As stated by Garibi, it is anticipated to become an integral milestone in the development of UAVs. Internet of Drones is defined as a layered network control architecture which supports UAVs in coordination. In the Internet of Drones environment, many drones combine and form a network while transmitting and receiving data from each other, as seen in this image. Understanding this is critical for analyzing the threats and vulnerability of drones from the perspective of communication. The ability for a drone to carry out its mission tasks fundamentally lives and dies with the drone's ability to communicate. As stated by Garibi, the communication incorporating Internet of Drones in numerous applications is another footprint for the next generation development of the future Internet, which may be used for next generation applications like smart tracking, smart parking, air traffic control, and cellular networks. Understanding how drones communicate will fundamentally also help us understand how to protect them. The threats that are specifically targeting communications are also heavily focused on the integrity and confidentiality aspects of the communication. In order to circumvent these attacks, the attacker or an intruder can compromise the keys and capture the communication, which leads to the breach of privacy. The attacker can target the vulnerability within the Internet of Drones and its application platforms to gain keys. The access to this information can be fabricated or modified by the intruder, which may misguide the receivers. Access control of Internet of Drones is a crucial parameter. Therefore, security concerns about access and authorization should be emphasized. The parameters needed for a security solution put forth for access control and application platforms will be further analyzed in the solution sections of this presentation. So next up, we have the big three. Now, why we are referring to it as a big three is there are three areas that we see that drones are vulnerable to being attacked. Those are hardware, software, and communications. So we'll start with communications. An important distinction to make is the vast encompassing of platforms that fall under the term UAV. An unmanned aerial vehicle is originally an aircraft that flies without any human pilot on board. Instead, its flight is controlled either remotely by an operator or by onboard computer systems autonomously. Often, UAVs are also referred to as drones. With advances in computing, communication, and device miniaturization, UAVs could also include other flying objects such as quadcopters, balloons, gliders, and so forth. The robustness of UAVs also presents a unique challenge of how to also have a robust system of security. However, security can only work as effectively as its known threats. At present, the security threats to UAV communications include the following. You have eavesdropping. Due to the lack of encryption and other protective mechanisms, the exchanged UAV information in the open environment can be directly accessed by an adversary. Injection. Without appropriate authentication schemes, an adversary can masquerade as a legitimate entity to inject false information on command. And then denial of service. Very similarly to personal computing, without the appropriate denial of service mechanism, a multitude of compromised systems attack a single targeted UAV, thereby causing denial of service for legitimate users of the targeted UAV. So when addressing these attacks, one major point to remember is that, as Girazani states, the increased security measures should not deteriorate network performance or affect the normal operation of the network. Therefore, in future research work, it will be necessary to achieve a good balance between the strength of the security measures and the performance of the network communication. Keep this in mind as we look over several solutions, as a statement is something the drone industry, and especially the security aspects of drones, has sorely missed.
We will compare two models of unmanned aerial vehicles, the Bebop and the DJI Phantom 4 Pro, for differences in the big three: communications, hardware, and software. In communications, the Bebop memory is accessed through its Wi-Fi connection and the use of communication protocols such as Telnet and FTP. The onboard flight controller controls the drone by combining input from several sensors, including a GPS chip, a vertical camera used for adjusting the Bebop drone's orientation and its XY position, and other sensors such as a barometer, accelerometer, and a magnetometer for assistance. The DJI Phantom 4 Pro makes use of orthogonal frequency division multiplexing, or OFDM. Its receiver module is responsible for pairing with remote control and communications. The OFDM receiver implements the Lightbridge technology and is also a middleman between the gimbal and the flight controller. The control signals and video is transmitted over a 2.4 gigahertz range using digital transmission. Ambarella makes a video stream to the DaVinci module via HDMI or USB, and at the same time writes a video stream to micro SD. The DaVinci sends video to the encryption module. After that encrypted stream goes to an RF transceiver. Hardware, the DJI Phantom 4 Pro operates using the Rockchip ARM processor and Unix-based operating system, BusyBox. It comes with a powerful remote controller that has Lightbridge technology. Lightbridge is a one-way stream of data with two-way handshaking, minimizing video development while maximizing flight distance. As a result, developments with the Lightbridge are more consistent at a distance versus standard Wi-Fi. Lightbridge is much faster at reestablishing a connection when it reaches a distance limit. The GL300 main board is the most important hardware component, supporting the processor, Ambarella, CPU, FPGA, Altera Cyclone V, micro SD slots, and radio transceiver modules. The Parrot Bebop 2 uses a P7 dual-core CPU, a quad-core GPU, and 8 gigabytes of memory, and the operating system is a stripped-down version of Unix referred to also as BusyBox. The software surveying the vulnerabilities found in Phantom and Bebop drones, including drone hacks based on unprotected Wi-Fi, access to drone configuration files, and changes to settings in flight and GPS attacks. Wi-Fi insecurity, the Parrot drones allow multiple connections through Wi-Fi, which allows an attacker to tamper with the system and hack the drone. Skyjack disconnects the controller by changing the SSID and immediately reconnects, and is then able to transmit commands through the malicious drone to the hijacked drone, enabling it to take control of another drone in flight using a customized script, hereby forming zombie drones. The DJI Phantom 4 Pro is not vulnerable to this attack, where the Bebop 2 drone is. Maldrone sets up a proxy serial port, intercepts flight commands from the controller, and redirects actual serial port communications to fake ports while forwarding the hijacker's commands to the drone. While the Bebop 2 will be affected, this attack is not applicable for the Phantom 4 Pro. GPS-based attacks. Drones use GPS signals for navigation. The GPS signals used by civilian drones are not encrypted, thus drones are vulnerable to GPS attacks. This section will discuss the 6 main attack surfaces through which hackers can gain unauthorized access or disrupt operations to a smart chip. The first attack surface is the positioning systems. Several positioning systems will be required to enable autonomous vessels to pilot safely in both open sea or shallow waters, such as for docking to a port. Many of today's ferries and maritime vessels are already equipped with sensors. And as ships get increasingly autonomous, it is expected that a vast array of sensor equipment and data will be necessary in order for decision-making systems to function properly. And next, there's firmware upgrades. Unmanned ships depend on the integrity of their systems, and therefore it is critical to ensure that the latest firmware is installed on the systems and that the deployment on board is secure. A voyage data recorder is an electronic system on board a ship recording all positional, navigational, and sensor information during a voyage. It's comprised of two parts: a data aggregating unit and a storage unit. If the ship becomes involved in an accident, the VDR can be subsequently used by investigative authorities to accurately determine the cause of the accident. And the next attack is intra-vessel networks. Traditional backbone ship area network, or SANs, are mostly wired by design to meet reliability requirements. For communication in wired networks, maritime standards call for the use of the controller area network, or the CAN bus technology, which has been developed for the automotive industry, in which CAN bus has simplified the addition of new modules and equipment without affecting existing cabled installations or networks. The CAN bus in a ship connects, controls, and monitors shipboard electronic equipment, instruments, sensors, and actuators. And the last attack is vessel to land communication. Existing maritime vessels generally are equipped with multiple links using both terrestrial networks based on high frequency radio waves or PP cellular standards, such as 2G, 3G, and 4G, as well as satellite networks. Both terrestrial and satellite communication can approach broadband-like speeds.
As discussed, attacks against drones and IODs can compromise confidentiality, integrity, and authentication in a variety of ways. I will walk us through 3 potential solutions to various attacks. First, I will discuss a blockchain-based architecture for drone authentication. Next, I will discuss a neural network-based solution to monitor drone state change. Finally, I will discuss an elliptic curve cryptography, or ECC, solution for secure communication between a user and drone. So first, the blockchain solution. IODs can face several issues, including high drone energy usage, unstable connectivity issues, and unauthorized access. The solution, published in the IEEE journal in April of 2021, has a goal to minimize the time spent authenticated drones within a smart city while maximizing overall security. As depicted in the figure to the right, a city is divided into several zones within the solution. Each zone has a drone controller, or DC, which manages all activities. The communication paths in this architecture include drone to drone controller to drone controller, drone to drone, and drone controller to blockchain. During drone registration, the drone controller generates a public-private key pair for each drone, and this information is saved in the blockchain. The public key is utilized for communication within the zone, and the private key is utilized for communication outside of zones and when migrating between zones. As drones migrate from zone to zone, they do not need to re-authenticate, which saves time. Next slide. So each block in the blockchain contains a key, a hash, and a list of transactions. A transaction includes an ID, the MAC address, the zone number, and a path info for a particular drone. An example of a block in the chain is depicted below. When comparing the solution to a generic model, the blockchain solution detected over 80% of UDP flood, SYN flood, TCP flood, and auth attacks. This is compared to generic models, which at best detects around 60% of these attacks, as depicted in the chart to the right. Next, I will discuss the Mini-Me solution. Mini-Me, which was published in the ACM journal in October of 2021, is a data-driven online monitoring framework that models the drone control state to detect runtime data-oriented attacks, such as sensor spoofing. By reverse engineering the control binary to leverage the drone's internal data flow and control variable dependencies, Mini-Me is able to train a neural network-based model as a replica of the original drone controller program. Mini-Me then runs this model to detect any deviations in the predicted control state and the actual control state, which can be the result of malicious activities. This solution has proven successful in detecting sensor spoofing, actuator spoofing, control signal spoofing, control parameter, and hard timer attacks. Finally, I'll discuss the ECC solution. So the elliptic curve cryptography model, published in the IEEE journal in September of 2021, secures communication between a user and a drone flying in a specified zone. The authentication scheme has 4 main phases. The first phase is setup, where the main server selects a private master key and a hash to create a public-private key pair. The second phase is pre-deployment, where the server registers all drones in offline mode before they are deployed in the IOD field. The server stores a generated ID in the memory of each drone before deploying them into the field and storing the parameters of the drone in the server's database. The third phase is user registration, where an unregistered user registers with the server to receive surveillance data from a drone. The user generates their login credentials during this phase. The fourth and final phase of the system is login and authentication. During this phase, the registered user is authenticated and shares a secret/shared key with the drone for real-time surveillance data. This authentication scheme has proven successful against user impersonation, man-in-the-middle, denial of service attacks, and much more.
So there were a couple areas when we were doing our research that we felt were not fully addressed. So to start, drones are very resource constrained devices. Implementing security algorithms such as blockchain, even in a swarm of drones, means adding some more storage capacity and computation ability on drones. This might end up reducing the flight time. Moreover, using blockchain for non-critical communication can be acceptable, but for the critical things like location coordinates, blockchains can cause high latency as of right now. Future research is required to enable the security algorithms, keeping the resource constrained nature of drones in mind. The gateway between drones, ground controllers, and satellites in drone communication are highly vulnerable to various security attacks. If the gateways are compromised, and then the whole network is compromised, even though the end devices are highly secure. Further analysis is required on how to secure the gateways between different hops in drone communication. Next, current blockchain architecture is highly limited in terms of the number of nodes in permission-ed networks and in terms of throughput in permissionless networks. Various consensus algorithms are being designed to support high throughput along with a large number of nodes or users. Lastly, a concept of multi and distributed controllers are being proposed in some works to overcome the problem of the controller being a single point of failure in SDN architectures. However, further work is also required to ensure secure and near real-time communication between different controllers in SDN. Lastly, to conclude, drone platform security is a critical issue, and we believe this research shows that there is much room for more than just a modicum of improvement. There are many areas: security, smarter tech, more dynamic tech, better communications, coupled with just more efficient technology that can be harnessed to create a next generation of drone technology. The arguments for improvement become apparent. However, there is certainly room to explore more efficient outcomes on all sides of the platform. The beginning of drone technology is very similar to the beginning of personal computing. The market is very much still emerging, and once several of these platform goals are achieved, the growth of the drone market will excel. This work shows that there is indeed technology in enough areas that an adaptive security-aware system for drones and Internet of Drone devices using machine learning and other cutting-edge technologies is possible. The security concerns that have limited drones in the past have been addressed through this research, and the necessary technologies in major areas have been mentioned. When the above security measures are taken, this will allow for a better drone platform to be possible. When we have a secure connection to the drone, as several of these works together prove, you can start to create a more secure system and thusly a better world. If anyone has any questions, feel free to leave it in the comments or reach out to us via email.